Everyone loves to ride the log flume at the theme park. In this ride, all gravitational potential energy gains are equal to potential energy drops around the complete loop. The biggest drop of all can lead to water flying everywhere and mechanical energy being converted into useless heat. An electrical circuit has many similarities to the log flume ride. Charges are analogous to passengers riding in logs. Batteries in the circuit take the place of escalators for the logs, and voltage drops across resistors in the circuit are analogous to the loss of altitude and energy by the logs going down the water slide. Kirchhoff's junction rule amounts to conservation of charge in a circuit and states that the sum of the currents entering a junction, or node, must equal zero. Currents entering the junction come in with a positive sign, and currents leaving are assigned a negative sign. Here, I1 minus I2 minus I3 equals 0. Conservation of energy is accounted for in Kirchhoff's voltage rule. Here, the sum of voltage gains and drops around any closed loop must equal 0. In this example of a single loop, the 45-volt battery raises charges to 45 volts of electric potential. Each resistor around the loop uses a fraction of the charge's energy until after a complete circuit, charges have the same potential energy they started with. In a circuit, voltmeters are used to measure voltage differences. Note that the red positive probe measures the voltage relative to the location of the black reference probe. Here they read plus 45, minus 10, minus 20, minus 15, all summing to 0 around the loop. The Kirchhoff junction and voltage rules are particularly useful for analyzing complex circuits, that is, circuits with multiple voltage sources and multiple loops. This circuit has 2 voltage sources and 3 branches with currents I1, I2, and I3. The current directions shown are guesses, and you can probably tell that whoever guessed the direction of I1 probably guessed wrong. But that doesn't hurt our analysis. It just means we are likely to predict a negative value for I1. Application of the junction rule yields the equation I1 plus I2 plus I3 equals 0 for the 3 unknown currents. Applying the loop rule to the loop on the left and summing gains and drops yields R1I1 plus V1 minus R2I2 equals 0. This may be rearranged into a standard form with the 3 unknowns on the left and the known voltage V2 on the right. The loop rule applied to the loop on the right gives a third equation for the unknown currents. We now have 3 equations for the 3 unknown currents, and this is enough. Plug in the known values of resistors in kiloohms, and plug in the known values of voltage sources and solve to predict the values of the 3 currents. Note that with kiloohms for resistance values, the equations predict currents in milliamps. You can use your favorite online linear equation solver to determine values for I1, I2, and I3. Sometimes predicted currents come out negative. I1, for the example shown, is very likely to have a theoretical negative value. Not to worry. Negative current just indicates that it was drawn in the wrong direction initially. Instead of pointing downward as shown, the current I1 actually flows upward through R1. To measure the currents, just remove a connecting jumper wire and replace it with 2 leads and an ammeter. Notice that the current as drawn should enter the red milliamp terminal and exit the black common terminal of the ammeter. Here are 3 adjacent resistors in the circuit board with 2 voltage sources connected and an ammeter measuring the current I1. This type of complex circuit with multiple branches and voltage sources is useful when modeling the cell membrane resting potential in physiology. Cells are bounded by a lipid bilayer membrane. A charge separation across the membrane is caused by the movement of ions such as potassium plus through the membrane, leaving charged protein molecules, labeled with an A-, behind and within the cell. The voltage within the cytosol of the cell is measured with a small voltmeter probe relative to the extracellular fluid. A typical value of the resting potential of a neuron is approximately minus 70 millivolts. The inside of the cell is generally at a lower voltage than the outside. The cell membrane has transmembrane proteins acting as passive channels specific to a given ion, allowing just that ion to diffuse through. Potassium plus, for example, has a higher concentration inside the cell than outside. The passive potassium plus ion channels allow potassium ions to diffuse from high concentration inside the cell to lower concentration on the extracellular side. Protein anions are unable to follow the potassium ions through the channel, leaving the inside of the cell negative, lower voltage, relative to the outside of the cell. This forms a type of battery or voltage source across the membrane. Eventually, the attraction of the negative anions brings the diffusion to a halt and an equilibrium is achieved. The equilibrium voltage for a specific ion is called the Nernst potential for that ion. The Nernst potential is computed using the Kelvin temperature T, the charge of the ion, Q, and the ratio of the outer and inner ionic concentrations. A larger ion concentration ratio leads to a greater magnitude for the Nernst potential. The potassium plus ion is not the only ion involved in generating a membrane potential. Sodium plus, chloride minus, and other ions also contribute their own Nernst potentials. The concentration gradients between the inside and outside of the cell are maintained by ion pumps using active transport powered by the ATP, adenosine triphosphate molecule. Sodium plus has a greater concentration outside, so sodium ions flow into the cell, yielding a positive Nernst potential. Chloride is a negative ion with high concentration outside, giving chloride a negative Nernst potential. Potassium ions have a Nernst potential of approximately minus 90 millivolts. The ion channels allow a current to flow, so they form a circuit branch modeled by a voltage source, a resistance that depends on the numbers of ion channels, and an ion current. Similarly, sodium plus ions form a circuit branch through the membrane with a large outside concentration leading to a positive Nernst potential. Note the orientation of the sodium voltage source, high voltage inside. Chloride ions have a large outer concentration but are also negative ions. They produce a negative Nernst potential. As part of their Nobel Prize-winning work, Hodgkin and Huxley developed the model circuit shown here to predict an overall cell membrane potential. The cytoplasmic interior of the cell is at the bottom. The extracellular outside is shown at the top. The voltmeter is measuring the cell membrane potential of the inside relative to the outside. The cell membrane is represented by the circuit, with each species of ion having its own Nernst potential, resistance, and current through the membrane. The three potassium, chloride, and sodium ionic channels form parallel branches of the complex circuit. Applying Kirchhoff's rules yields four equations involving the three unknown currents, as well as the fourth unknown, that is, the membrane potential V sub m. Mathematically, we can eliminate the currents and solve for the membrane potential. The resulting expression for the membrane potential is known as the Goldman equation. Each ion's Nernst potential and resistance contributes to the overall membrane potential. The greater the Nernst potential and the smaller the resistance for a given ion, the larger that ion's contribution is to the overall membrane potential. By defining conductance G as the inverse of R, we see that the membrane potential is just the average of the Nernst potentials, but an average that's weighted by the conductance. You can construct the cell membrane model circuit using the resistor board and three voltage sources. Note that the voltages are scaled up from tens of millivolts for an actual cell to volts in the model circuit. Pay particular attention to where you connect the positive red poles of the voltage source. If you don't have three voltage sources, a 9-volt battery can substitute for the 9-volt source. An axon is a long, narrow extension of a nerve cell that transmits signals rapidly down its length. sometimes as much as a meter. There's not sufficient time for currents to simply flow from one end of the axon to the other. The action potential is a voltage signal sent from the cell body down the axon to the terminal. If a voltmeter is placed at some point along the axon, it measures a time-dependent action potential as it passes that point. Within a couple of milliseconds, the membrane potential changes from its resting state of minus 70 millivolts, depolarizes to a relatively large overshoot positive voltage, repolarizes to a large negative undershoot voltage, finally returning to the resting membrane potential. The important features of the action potential are modeled with the same circuit, but with adjustable resistances for each ion. The arrows on the circuit indicate resistors that can be dialed up or down as needed. The devices responsible for adjusting membrane resistances are so-called voltage-gated channels. Depolarization occurs when a threshold membrane potential of approximately minus 60 millivolts activates sodium plus voltage-gated channels to open, lowering the resistance for sodium ions. As a result of additional pathways, the sodium ions come surging through the membrane, charging the interior of the cell positively and leading to a positive membrane potential. This graph of conductance with time shows the effect of first opening and then closing the sodium voltage-gated channels. Opening channels reduces resistance and enhances conduction for sodium ions. In the extreme case where sodium ion resistance is negligible, overshoot is achieved and the membrane potential becomes approximately equal to the plus 60 millivolt sodium Nernst potential. In our model circuit, overshoot is simulated by placing a jumper wire across the sodium resistor and shorting it out. The voltmeter then reads the scaled up Nernst potential for sodium ion of plus 6 volts. I know it requires courage to short out a circuit, as shown by placing the shunt wire across the sodium ion resistor. But it's okay, as long as you don't short out two branches at once. Repolarization is a rapid reduction of the action potential to negative values. Repolarization results from a closing of sodium voltage-gated channels and a corresponding opening of potassium voltage-gated channels. Then the potassium ions pass freely through the membrane and out of the cell, leaving the interior of the cell very negative. The conductance curves of the two ions are shown here. Note the rapid drop in conductance for sodium ions and the gain for potassium conductance as voltage-gated channels close for sodium and open for potassium. In the extreme undershoot situation, so many potassium ion voltage-gated channels are open that the potassium ion resistance is effectively zero. Then the overall membrane potential is just the potassium Nernst potential of minus 90 millivolts. Undershoot is represented in the circuit by removing the shunt from the sodium resistor and placing it across the potassium resistor. Try it in the actual circuit and note that the overall scaled up membrane potential drops to minus 9 volts. To summarize the features of the action potential, a small section of an axon begins at t equals 0 in the quiescent resting potential state. A small voltage stimulus boosts the membrane potential above the threshold for voltage-gated sodium channels to open, allowing the positive sodium ions to flood the interior of the cell, charging it positively and depolarizing the membrane. At overshoot, the sodium resistance is nearly zero, so the membrane potential is similar to the sodium Nernst potential of plus 60 millivolts. High voltage levels within the cell causes sodium voltage-gated channels to close and potassium voltage-gated channels to open. Potassium ions surge out of the cell, lowering the inside voltage, repolarizing the membrane. At the extreme, potassium ion resistance is nearly zero, and the membrane potential is approximated by the potassium Nernst potential. Finally, all voltage-gated channels close. The sodium-potassium ion pumps get to work to reestablish the cell resting potential.